that comes from SQL. All right, so, okay, it's 4:10. So what I'm gonna do is let's spend a little bit of more time on the visualization now. And we're gonna be selective here. Anything that can be visualized in R, okay? Let's put it bluntly. There are hundreds of visualization libraries in R. The coolest picture you've ever seen in a magazine, it can be done in R. There are packages for that. Things like word clouds. You guys are familiar with word clouds? If you have a bunch of text, like an abstract, and you want to see which words are the commonly occurring or co-occurring words, you can do one of those wordos or word cloud diagrams that kind of highlights in different colors, different phrases and whatnot. You can do connectograms, circles, connectograms. Have you guys seen connectograms? We use them quite extensively for genome-wide association studies. We're going to show you some of these later. They can be done in R. Obviously, all the distribution plots, variety of things. So here,
I actually have a question about that.
Yeah.
So is the visualization that's being done underneath C or C++ for that?
Right. So and that's a good question. How is the visualization actually done? The answer is yes. Some of these package visualizations are done in a foundational language, and R is simply the syntax for invoking the graphics library, and that's why you need a system-specific R bindings, because the visualization package is going to have a Linux distribution, PC distribution, and a Mac distribution, and that's where the graphics card comes into play and all that business. Same thing with Plotly, by the way. The way we did Plotly, there is well, I'm actually not sure how Plotly does it. I think it may be using the WebGL that we used earlier for the brain visualization, but it could be done with the standard OpenGL, which is the C library for visualization. So many of them are done natively. Some of them could be interpreted as well. So it's difficult to say exactly in general. Okay, so here's a list of, it's difficult to classify visualizations. I have tried here to give you a little bit of a hint as to what types of visualization tools are available, tools for composition, distributions, relationship, and comparisons, and all of these are available for single or multiple factors. Here are some examples of these that are present down. This is a more interesting example that I want to show you, the brain region. It's a visualization of a single brain slice, but it's clever because it shows you almost like confidence limits. It shows you in 3D the renderings of the either neighboring slices or perhaps the amount of variability between subjects you can show as well. So you can do a lot of really cool interactive visualizations using various plugins. So, okay, that's a cool example. It shows you how to overlay, just like we did in the soccer demonstration that I did earlier, the histogram plot with the model on top as a smooth density. Very simple. You plot the histogram first, and you simply superimpose lines of the density of X. In this case, I'm plotting the same things as raw frequency histogram and as smoothed density line. Okay, here is for another data set, pie charts, here is the soccer letter frequency data. This is an interesting data set if you want to look at. It has, for all the Roman-derived languages, I think there are 25 common characters, because many of them do have special characters. For the 25 common Latin letters across the Roman-derived languages, what's the distribution of the letters, of the common letters? Think about the vowels. A, E, I, these things. And they're surprisingly different in different languages. So you can look at this download the data, plot some of these. So here I plotted, for example, the English just for the English letters, pie charts, and they can be made more fancier. They could be three-dimensional, moving, non-moving. You can pull a slice of the pie chart. You can go crazy with these things. I'm just showing you some very simple examples. Most of the charts in R have specific delimiters. SEX tells you the size of the font that's going to be used to label the chart. Point character type says what kind of things. So some of the legends, font sizes, etc. And these are the heat maps that I mentioned earlier. In genome-wide association studies, these come up very frequently. So here is, for instance, for an Alzheimer's disease cohort, you are looking at single nucleotide polymorphism references as the rows, and then the columns represent 60 or so brain regions of interest, okay? And the hot areas are where you have high associations. Think about high correlations between a genotype and a derived neuroimaging biomarker phenotype. So the hierarchical clustering that you see on the side kind of tells you how are these genotypes or correspondingly regions of interest similar. So you see, it kind of gives you at a big level, there is two groups of AD neuroimaging markers, group 1 and group 2. Now each of those is subdivided. When it comes to the genotype, the story is a little bit different. Well, maybe not so much again. You do seem to have one cluster of genes that have these SNPs in them, and then the other ones over there pretty much, a lot of nonsense, not very heavily dependent. But again, this is a two-dimensional histogram. It's constructed very easily using the heat map plot. It takes in a matrix. You guys can look at these matrices. They're available right up here on this site. I don't want to download them right now, but 3 matrices, one for the AD cohort, one for the mildly cognitively impaired individuals, and one for the controls. These correlation plots, we've done the imaging parcellation, we've done the genome imaging associations, and these matrices simply have the strength of the associations in them, and then whatever it said, 80 by 60 or something like that. So AD, MCIs, and controls, and you see that these are different plots for multiple reasons. First of all, when the heat map is plotted, we are letting the hierarchy determine the order in which the SNPs and the imaging IDs are included. You can also force them to be in a very specific order, because what I'm saying is that these 3 charts are not directly comparable because the rows and the columns are mutated. Is that right here with me? But you can force them to be in alphanumerical order, and then the results are going to be comparable. But then if you do that, you're going to lose the hierarchical driven association part. So is everybody kind of with me here? So you can play with some of these. They're very useful. Scatter plots, you have 2 variables. See, in this case, uniform variables plot one against the other. That's the scatter plot. That's a beautiful scatter plot for residuals. If you have some kind of a residual scatter plot like this, you're happy, no patterns. And indeed, in this case, they are indeed random. You can also use ggplot, just like we did before, to do a qplot, where, you know, here you can see that the categories have different colors associated with them, and the size of the blob corresponds to, in this case, a fake variable. We're just multiplying the x values by 5, and this kind of gives you the size. But I can actually show you. We have developed a motion chart that can render really nicely up to 7-dimensional data set in a very clever way. So let's just go to soccer. Maybe that's worth doing. Soccer.umish, and under web apps, motion charts, there are a few data sets that are already pre-coded, but of course you can just copy paste here any data set, as long as one of the features in your data set has to have a time-like characteristic, because motion charts are intrinsically moving charts. And what do you move about? Well, you move the time slider. So it doesn't have to be time. It could be, I don't know, hospital ID, or I don't know, longitudinal measure or something like this, but it needs to be an ordinal variable, preferably time. So you can, all these guys you can remove, copy, paste, and all that, plug in new data if you want. I can show you later. In this case, it just defaults to the housing price data, because it's a nice demonstration. It has a categorical state variable, and this is for the US, but you can imagine this for any other country, and you can imagine these guys being hospitals across the year, and then you have performance measures. In our case, you have housing price index, unemployment rate, region, this could be a state within a country, and then population size, and then percent I forget what. Oh yeah, interest. I'm pretty sure this was the interest rate. Okay, in this location. So in this case, we were interested in looking at whether the housing. Think about it. I mean, if you're looking to buy a house, what do you want to know? Well, the first thing you want to know is, what is it going to cost me? Not the base price of the house. Forget about the base price. You're talking about the interest you're going to be paying. And interest is very heavily dependent with this annual percent rate. You know, what region is the house? What's unemployment rate? If the unemployment rate is high, are you going to be shopping for a house? You'll be crazy to be buying a house when the unemployment rate is heading up. You know, so 1, 2, 3, 4, 5, 6, 7 or so variables. So look what's happening here. Now it's set to auto rotate. Okay, and you can select various things. Okay, California is the big behemoth in the US. High prices, high population, you know, everything is high there. But there are some small states as well that I can choose. This is Washington, D.C. And you see what's happening, right? Let me see if I can scroll down a little bit. Okay, here's the time measure, you guys. And the indicator over it kind of shows you from, this is the year 2000, 2001, etc. You can see, that, I'm sure it was the same here in Southeast Asia, right? There was a housing boom that led to the greatest recession since the World War II. You know, it was crazy in the US, and I'm sure you guys, when the US sneezes, everybody catches a cold or whatever it is. So look at. So right now we have housing price index on the horizontal axis, which means that the price of the homes is increasing rapidly with time, and on the vertical axis I've got unemployment. So look at the huge drops of some of these states. Okay, so you can kind of get an interpretation of the dynamics here. Unemployment rate is going up and housing prices are going up. What kind of a world is that? You know, it's a crazy world that led to the bust. That kind of world. But you can see that not all states are created equal. I mean, you know, what is this here? Why are they so expensive? Well, Massachusetts, okay, you know, and I'm sure New York is here somewhere as well. But you can see the dynamics. Now, this app is pretty cool because not only that, you can select. So, for example, the key is the thing that you want to move the motion chart over. And then you have x-axis. You can select any of these variables to be your x-axis. So, for example, I can select x-axis to be the interest rate. Okay, unemployment on the y-axis, that's fine. Population is the size of the blob. Okay, and then you guys, I can introduce transformation. I can introduce a log scale on one of these variables. Okay. Just get rid of this. There we go. So, again, I introduce log scale on the size. Okay? So you can do a variety of things and essentially visually explore multi-dimensional data set, which is difficult to do when you look at 2 or 3 variables. Here you have color, size, x, y, and time all come into play together, right? Okay. So
that is done in R?
No, this is done. This is a very clever chart. It's purely done in HTML5 and JavaScript. This has nothing to do with R, because the intent here was to have a tool that you don't do any coding. You just go to data, remove all of these, Control A, remove all of these, and plug in your own data. You know, so there is no coding here. The coding happens when you say which feature gets mapped to what behavior of that, right? That's the coding, but it's graphical. It's not scripting based. All right. So, you know, I would love to do all of the apps in HTML5, but you can imagine it's not that trivial because R provides a lot. Coding in R is easy. People have done it. You just need to package it. Coding in HTML5, not so easy. Somebody needs to go ahead and do the functionality. All the statistics need to be done. All the, you know, the rendering needs to be done. It's not as, it requires a bit more work. All right. So scrolling down here a little bit. Oh, pairs. This is very useful if you have data sets that have multiple features and you want to look at them collectively and find out if things are highly correlated. Because remember, if most of the parametric methods, including all the linear models, require that your features are independent variables. And if you have a feature, well, I don't have any here in this plot, but if one of these was a very heavily associated plot with all the dots kind of in a not linear, but ellipsoidal fashion, right? This would suggest a strong collinearity, which means that one of the variables needs to be dropped or manipulated in some way. So you can generate dozens of these pairs in literally one-stop shop. You kind of eyeball them and you say, fine, 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 it's all fine, or look at these 2 pairs. It zeroes down exactly on bivariate but not trivariate relations. So sometimes X and Y drive Z up and you're never going to be able to see it with pairs. Right? Does everybody get it? Because you actually need to have another dimension. That's why the motion charts come in, and after 6 or 7 dimensions, it kind of becomes blurry. Okay. So here's one, okay, yeah. So this is a good example. Now look, some of the data here are dichotomous, just two values, you guys. Okay? Yes, and now here you're coming across two dichotomous variables, and they are post-traumatic stress disorder and GLBT are the two. So every one of these, you kind of look at the column name and the row name, and then the scales are listed. The scales on each axis are listed either on the top or on the bottom. Right? It takes a little bit of getting used to, but these are very useful charts. Here is a plot where you want to plot a model, a nonlinear curvilinear model with the confidence limits around it. Obviously, the confidence limits widen up as you reach the end points of your spectrum. That's to be expected, right? Because the uncertainty increases towards the outer bounds. The uncertainty is very low here because you got a lot of data. But towards the end points, you have fewer data sets, and therefore the uncertainty is higher. This is again the earthquakes data set that kind of shows you how you can label the depth, for instance. I don't know if you guys know or care about it, but earthquakes that are deeper underground tend to be stronger in reality, but the impact is less on the surface because obviously of the cushion in between. More superficial earthquakes that are close to the surface, they can be lower magnitude but devastating because they shake too much. And obviously there is lots of other things that. But this is a plot of the depth versus latitude, and then the magnitude type was listed as a different color. Here's another one, depth versus, and you can also list the specific locations of these. These are the indices instead of just dots. This is the 119th record, 80th record, etc. You can only print the IDs of the events, etc., etc. Bar plots. These come in useful when you have categorical variables folded in. So remember, these could be different diseases, and then within the disease, you may want to have racial distributions or something like that to see if there is gaps or differences. And in this case, it's interesting because we are also reporting the actual values. These could be replaced, by the way, with error bounds to show you, because when you see two of these, it shows you, in terms of their means, they're different, but are they statistically different? You have zero evidence because you don't know if the error bars are tight, these are going to be different. But if the error bars are huge, then these could be statistically indistinguishable, even though they look different, and vice versa over here. It's just not clear of how much significance is present. Here are the error bars if you want to do that. And if you want to print the values, legends can be printed using the legend command right up here. After you do the bar plot, you essentially put a text on it, and the arrows represent the confidence limits. So these are mean plus standard deviation. Sometimes this may be 2 standard deviations away, whatever you want to, but you got to be clear what the error bars represent. Are they standard error of the mean versus the standard deviation? Does anybody know the difference between standard error of the mean and the standard deviation for one sample? So suppose you have a single sample, okay? You can compute the mean and the standard deviation, right? We know how to do that. The standard deviation is a measure of dispersion. So if these bars represent standard deviations, it means that on average, people scored 9.91, give or take 1 or something, okay? Let's pretend this is 1 unit. But if you want to look at the sampling distribution of the mean, okay, the sampling distribution of the mean has a standard error of the mean, which is the standard deviation divided by square root of the sample size. Okay, which is totally different because this 1 unit now for a sample of 100 is going to give me square root of 100 is 10, and I'm going to have to divide this one by 10, and this is going to shrink all the way down to 0.1. So the standard error of the mean limits are always tighter, okay? But they represent completely different things. They represent what would happen if I reran the experiment and recomputed the sample average. How far away is the sample average likely to be? Not how far apart are random observations in my study. Is everybody here with me? The standard deviation tells you how far apart are individuals within the same study. The standard error of the mean tells you how far apart is another study under the same conditions, how far apart is the mean going to be from the mean that you observed before. Okay? And means are always closer together. Individuals are not. Okay, so here's another example. Colors. Trees. Okay. Oftentimes, you have hierarchical structure. Data representing hierarchies. These could be, I don't know, kin relationships within a population. If you look at the parents or the offsprings or something like this, you have some kind of a hierarchy. You can have, a variety of things. And in those cases, you may look at, data that kind of looks like this, right? This is a cluster dendrogram that illustrates, depending upon what height you want to cut it, how many populations are there. So if I cut it over here, there will be only 3 populations. Population 1, population 2, and population 3. But if I want to cut it over here, there will be 1, 2, 3, 4, 5 populations. And as you go all the way down to the individual, you do the stratification on the individual level. So obviously, useless, well, somewhere in between there is use. But where is in between? Well, that's a tough question. It depends upon, do you have any a priori knowledge about how many clusters are there to be expected? And we'll talk about clustering. There is a bit more that we're going to talk about it later. But this is just how to visualize some of these things. You can cut the tree to make it simpler. And it shows you how many subjects end up being in the leaf nodes at the end, terminal nodes in each of these branches. Correlation plots. These are very nice. So the very same data that we looked at the heat maps for, the two-dimensional histograms, is rendered in terms of these correlation plots. Core plot is the method. You can use circle as the type of method. And you see higher correlations are either dark blue or red or kind of red spectrum. And their magnitude is related not only to the color but to the size. So high correlation between region P60, whatever it is, and P28. These are low correlation, slightly negative, the pink. There isn't strong negative correlation here. They're either strong positive or weak negative correlations. The one that I like a lot from this, there is variance, okay? That's an interesting one that reminds you almost of the tensor tractography in a way. Perfect correlations, lines, as they become less strong, they become ellipsoidal, and ultimately when they become a circle, it's, not very impactful. You can see the pink kind of in between, weak, but weak correlations, but somewhat present. And there is one here that shows both. Yeah, That's an interesting one. It didn't render too well on the HTML, but you can imagine. By the way, a correlation matrix is always upper, lower diagonal symmetric. Okay, so it's a symmetric matrix. This is a nice plot. Again, it didn't render too well, but it shows you the value that corresponds with this. Okay, so this is 0.56 corresponds to this one over here. This one, strong correlation corresponds to this one. You know, the weak one over here, etc. So we can see both the magnitude as well as a visual depiction. All right, so there is more density plots here. Oh, so let's just look at this. I'll skip over that example. And look at this two-dimensional image surface plot. So you guys can probably try this right now on your computers. This would require the JPEG library for loading and understanding rasterized images, two-dimensional, not 3D, we're going to get to 3D later, two-dimensional images, JPEGs, TIFF, PNGs, GIFs, you know, all the rasterized images that you see online can be loaded in with this. I've put in one data set over here. You know, you essentially generate a random file name locally. This URL address is sent to download file, and write binary file, writes it as a binary file in this location. This is a useful command if you want to generate in your system a temporary file name that you don't care about what it's called and you want it to be wiped out once you close the R session. Okay? So it generates a random file name, and in this file name we're going to read from this URL address and write binary file, and then we're going to convert that. The read JPEG image is part of this library, so we read this file as a JPEG image, and that's my image, and then printing the image info is going to report for you, for example, what's important in an image. Well, its size is important, its width, its height, and its intensities, I guess. Okay, so right up here, we're extracting, because this is apparently this is a multi-channel image. I'm extracting, remember this syntax, we already talked about this. It means all the rows and all the columns, but only take the first plane, which represents one of the RGB channels, and render it as a now two-dimensional object. It used to be three-dimensional JPEG. And then we're going to convert this as an image. We're going to blur it a little bit, and I'll show you in a second why we're blurring it a little bit. So blurring essentially convolves it with a Gaussian filter, kind of a smoothing kernel that goes around and smooths a little bit because the image is a bit noisy. And if it's too noisy, remember when you render it as a surface, it's going to be a bit too spiky. And then make a matrix out of this. And then here is the interesting part. Here is where you can plug in the top level confidence limit and the lower level confidence limit, or you can plug in the slice next to it on the top and the slice next to it to the bottom. I'm simply simplifying this for the purpose of demonstration. I'm shifting the original image up by 1 for Z2 and shifting it down by 1 for Z2 just to mimic upper and lower bounds, okay? And then you're going to call the plotly package, and then you're going to provide the original image you want to plot, and then add a trace to add these surfaces on the top and on the bottom, and that's what you end up having. Now look at this. So this is an interesting brain because it obviously have very high hyper intensities here. This is a tumor that's being excised in this individual, and you can see again the intensity, and you can see how is it you see, because I remember I smoothed you guys. Remember how I smoothed the image? So that's the smoothed version. That's the smoothed version. I just offset it by 1 so that I can kind of peek right in between these to look at. But you can imagine that this could be actually the entire brain stack, except that it's not going to be very pleasant to navigate because a typical brain scan has about 100 slices. And imagine having 100 of these stacked on each other. It's going to be tough to look at. But a few of these you can kind of handle visually. And again, the usual, you can actually dive all the way in, explore some of these. I typically take, for papers, you can take snapshots at appropriate angles. Oh, and by the way, these are called isocontours. The isocontours are very important. They're essentially showing you the topography of the image. It tells me that the points that are on this line are at the same height. It's almost like a topographic map, right? Has everybody seen topographic maps? Or you guys do it on the phones now? You guys are too young. You don't know what topographic maps are, do you? Has anybody seen a topographic map for real? Some of you have? Okay. So, I remember as a young child, my dad takes me in the mountain and he says, let's look at the map. And I'm like, what is this? Lines, curves. Well, the lines are closer together, it's a steeper ascent, right? And if the lines are sparse apart, it's flat. So I said, makes sense. So same thing over here. So, it kind of shows you, and you can do this here as well, but the actual image is too jagged for you to get a lot of interesting information. Where on the smoothed image, you see, you can kind of see a profile. Does everybody see a profile here of the surface? Almost like cutting the surface and looking at the one-dimensional now distribution. So these are very clever ways that you can do this in plotting. By the way, in some browsers, I know in Firefox, the dynamic visualization I'm showing in 3D may not work. That's why I've included here a static image just in case your browser doesn't render it. Now, let's talk about 3D now and 4D. Or do we have to go? Are you guys ready to go? Why don't we just do this and we'll call it a day. Just this one last thing. There is a package called BrainR that can be used for, again, install packages. BrainR is going to load it and put it into the environment. And I've put in a test brain nifty volume on this website. You can download it exactly the same way that we did the two-dimensional image earlier, specify the URL, provide a file path, but now I'm explicitly stating a temp directory, put it somewhere, I don't care where, give it this name, and then download the brain file, and this method, read nifty is part of the BrainR package. There is many, okay? There's many packages for many things in R. This is just one example that you can read the nifty file. And then you can report its dimensions, 181, 217, 181. For those of you that have done brain mapping for a while, you know that this is the ICBM 305 brain atlas space. 181 in the X, 217 in the Y. X, Y, Z, right? You print the volume dimensions, three-dimensional volume, three-dimensional sizes. And then, okay, so now, maybe I need to do this because you can't really see that here, can you? Yeah, you're not going to be able to see this, so maybe I need to show you that. Okay, let's see. This is a bit different. So I'm installing and loading the BrainR package at the same time. Now look at all the dependencies, you guys. It says, I need all these things. Well, no problem, R. Deal with it, install them, configure them, download them, so whatever. So it's going to do it. It's only done once on every machine. But now, at runtime, you have to load the library. So, okay, while R is doing this, we're going to go back Wait, were we here? No, here, okay. And I'm going to try to run these things and then go directly to the contour 3D. You see quite a few packages need to be downloaded, unzipped, installed. So remember when I talked about cost of ownership? It's called total cost of ownership. Well, that's part of that. So you're your own administrator here, but you know, it's not too bad. Our studio does it for you. This button is important. You may want to stop. Sometimes you see when we get deeper into the machine learning, there will be some processes that run for hours, maybe days. You can stop them, you know, if it goes out of hand. You can also use session, restart R, terminate R, interrupt R, but be careful because once you interrupt it, you lost the whatever time elapsed calculations were done. You kind of puts a break and that's it. It opens your window, but you lost the compute things. Occasionally you guys would have to check for updates. One thing to remember, R, the fundamental R kernel, the R environment provides updates, that is new versions, about once a month. You don't have to get an R patch every month, but you probably will have to update your R version a couple of times a year, every 6 months or so. Because pretty soon you're going to be going out of sync. And it's just like with the operating systems, right? Imagine you've been 2 years behind, viruses, support, you know, it goes crazy. So you should keep your R version certainly not older than a year. R is easy to update, it's one click, update, boom, done. R, however, you need to update by downloading the latest version directly from CRAN, the way we did earlier. And also keep in mind that when you update, you see this button over here, check for package updates. When packages are deployed, the developers are asked to keep them current, which means that when R distributes a new version of the core, the package developers within a few months would have to update there to be consistent, you know, with the rest of the world. So when this thing happens, one of two things can happen. First of all, you updated your R version to the latest version, but the package is not updated yet, and now you're in this territory where the package doesn't want to run because the R kernel is newer. So that's a problem number one. Not a big deal typically, because remember, well, okay, this is just finished, but I want to show you this. Right up here, oh, and I don't know where this is on a Mac. I've looked at this on a Mac. There is a way on a PC right up here to select which version of R you want to use, and it's got a drop down. I can go down to version R 2.0, 3, 3.4. You know, you select the version to be compatible with the package that might not have been updated yet. So not a big deal. On a Mac, I'm not exactly sure where that, it's supposed to be up here on a PC, but it's somewhere else. It looks exactly like this, but it's for which version of R you want to use. I'm sorry, I don't know where it is on a Mac. Oh, and now I cannot close this. Oh my goodness. Okay. Well, that's the problem with screen sharing. I cannot. Oh my gosh. Okay, I have to maximize the thing to get this. Okay, cancel. So there is an update somewhere. Okay, so we got this loaded. So let me see what we needed to do next. Escape, or how do you exit the full screen here? Okay, there. So what I wanted to do next is I wanted to actually load the data. Right, does everybody see that? So I'm loading the data, printed dimensions, and then calling 3D contours. And now this may take, okay, the data is downloaded. Oh, it's being downloaded right now. Then the rendering, I believe, takes maybe 30 seconds or so. And it's an external window that shows up. That's why it's not in the HTML page that you saw earlier, because it's an external window. It's not printed in the plotting canvas. Oh my gosh, that's 7 megs. Okay. All right, so that's good. So now I'm in the business of rendering, so we gotta just be patient here. The file is now loaded, so it's rendering. Okay. And you see these parameters here are important parameters. Alpha tells you how opaque you want that level 20 intensity to be. So remember, you guys, it's almost like the topographic ISO contours. These are called ISO surfaces. At the intensity level 20, we're not going to be doing an ISO contour. We're going to be forming an ISO surface at the intensity level 20, and we're going to make it, alpha is pretty opaque. No, alpha is a transparency. We got to look at the documentation, okay? So, alpha okay, alpha is the channel level, a number between 0 and 1. Alpha typically refers to opacity. You know, opacity and transparency are exactly inverse of each other, right? Something that's fully opaque is 0, is not transparent, and something that's transparent is not opaque. You know, so they're kind of the opposite. So I'm not exactly sure what it corresponds in this case, but level 20. And now, where did it go? Right here. And this, by the way, is our graphics language. You can it is supposed to, maybe I'm not doing it right. It is supposed to, is anybody able to, it doesn't rotate. When you click on it, it's supposed to navigate it in 3D. It's not doing it for me, I'm not sure why. Let me try it one more time. If it doesn't work, not a problem. It should allow you to navigate the way we did with the brain viewer earlier. Now, in this case, you guys, I'm specifying two ISO surfaces, one at level 10 and one at level 120. And for this image, if you actually load it in a standard brain viewer, you see that the intensities, I believe, are between 0 and 256. So I'm taking two ISO surfaces, one at the lower intensity spectrum and one at the higher, and they're going to be rendered with different colors so that I can see, hopefully, two shells nested within each other, right? It's very kind of with me. And I'm using two different opacity levels for both of these. Okay, so I think it's rendering now, which is, okay, there we go, something is happening. Okay, so I know this may be hard to see. Okay, notice the extra 3D text that we put in to orient ourselves as to which one is the left and which one is the right hemisphere, where is the top and where is the bottom of the brain. Okay, well, I can't get it to rotate. Oh no, there, wait. There we go. It rotates, it's a bit clunkier, but right, you guys can see it how it switches a little bit. The text always stays where it needs to stay, right? On the top or on the bottom, because it rotates the three-dimensional scene. And the yellow and the red colors correspond to the two different layers that we had, 10 and 120. So, okay, so that's the structural volume rendering. And now for fMRI, there's a little bit more later in chapter 18 that I showed you about fMRI. Here is another fMRI that I've put together. You can download it, a single file, pretty much the same way. You read it as a nifty file. The dimensions, 64 by 64 by 21. Mind you, much poorer spatial resolution. In fact, it's 4 by 4 by 6 millimeters apart, almost half a centimeter voxel resolution, which is big, but it's pretty good temporal resolution, 3 seconds apart. So you have 180 volumes, 180 three-dimensional volumes, right, as a time series. And I'm just showing you here how you can print the time dimension volume and then go ahead and render the fMRI for what, you know, just this is just one time point render. That's what it looks like. Poor spatial resolution. You're going for the time here. You can also plot a histogram of the entire volume. This is oftentimes useful, remember, to tease out background. You know, how should the image be thresholded? For those of you that have looked at fMRI, obviously there's a lot of background here. There is a little bit of signal in the lower intensity spectrum, and then the higher, and then the rest is probably just noise. You can also use orthographic imaging to place the cursor in a specific 3D location. Okay, and that's what it looks like. You can plot, right, so you can extract, look at this. Stat fMRI test is only going to include the fMRI intensity that exceeds 15,000. And that's what this distribution looks like. A very nice, rapidly decaying distribution of intensities. You can also overlay, so this is the fifth time point, the fifth volume. Notice how we are doing X, Y, and Z, all of them. and that's why it's rendered from the inferior part all the way up to the superior part over here. From the bottom, kind of going like this, snake-wise, all the way up to the top. Yeah.
Some library which can help in storing and some missing options.
Are you saying that there is a library, or asking which library?
Yeah, which library, or if there is a library, I'm not
The nifty images are going to have intensity at every voxel. Now, if you want to have a voxel analysis, for example, later I'm going to show you how to pick a location and extract the time course of this location. This can be done on a voxel by voxel basis. And there's a lot of libraries, to be honest with you, so I'm not exactly sure of the specific functionality you're referring to, but it...
Smoothing is basically excluding the noise, so for that is
Right. So there is many fMRI analysis packages, including smoothing spatially with a Gaussian kernel. They typically use, I don't know, a 6 to 8 millimeter filter to go about. But you can also smooth in the time space as well. So yes, there are packages to do that. So here is, okay, I actually went ahead and, okay. So look, you guys, x1 is going to be a column vector with labels from 1 to 180. This is a sequence of empty things. 1 to 180 are the indices of this. And then we are going to be extracting, look at the time is blank here. The fourth dimension is not listed, which means that all the time points, we're going to extract location x, y, and z for 180 time points. And what we're going to do is we're going to fit a smoothed version of this. Y1 is going to be lowest regression smoothed version. And then we're going to use a different smoothed version for the same one, and yet another smoothed version with different kernels, right? Gaussian, normal, bandwidth, you know. So 3 different models for the same time series analysis, and they're kind of overlaid over here. So the blue is the raw time course of that specific voxel location. The red is the smoothed version. The green is K-smooth. Okay? And you can see that what I mentioned earlier, the fact that the noise level by far exceeds the actual paradigm effect here, which is typically on the order that you see up here of the smoothed versions. So there's quite a bit of noise, and you can see the denoising that's done totally on different scales by the 2 alternative smoothing packages. And more is in chapter 18. All right, so that's probably a good place for us to stop.